Okay, so this is just another way that you can find the solution set of for multiple solutions in a dependent system of equations. And thank you to Toby Harvey for pointing this one out. It does tend to work best when the line of intersection is a simple one with coefficients of 1 for the variables. But obviously, you can use it anytime. So I'll just go through the example and you can see how it works. So I'm just going to number the equations to begin with. In fact, I might even zoom a little bit so you can read more easily. And I'll create a fourth equation here by, let's say we'll do equation 1 minus 3. So we'll find out where those two planes intersect. So we'll get y plus z equals 15. So we know that planes 1 and 3 meet at a line. So we'll establish that much anyway. And then we'll just have a look at planes 1 and 2. So I'll go 2 and take away 2 lots of 1, and you'll see that all the x's, y's, z's all disappear, and 80 minus 80 is 0, so we get a true statement. So therefore planes 1 and 2 are the same. So what that means is that we have the situation where we have plane 3 coming through, and it cuts right through, that's a terrible drawing, but anyway, another 2 planes, like so. So this is planes 1 and 2 down here, and that is plane 3 cutting through. This line is where our solutions are going to be. And that line is the line y plus z equals 15. So probably the easiest way to do this would be to do something like going, all right, well, if we make a parameter t, let's just pick one of those variables, z, and make it equal to t. That means that y, in terms of that parameter, will be 15 minus t. That's just rearranging that equation there. And then all I have to do is substitute those two into one of our earlier equations. So I'm just going to do equation 1. So that's going to give me x plus 2 lots of this y. So that's 2 lots of 15 minus t plus 3z. So that's 3t equals 40. And I can rearrange this. So now I've got x plus 30 minus 2t plus 3t equals 40. And so I have an expression for x now, which is going to be 10. And what's that there? That is 1t minus t. Okay, so that's my solution set. I just have to get the range of acceptable values now for t. And you can see that x certainly can't be any less than 0, because if it went less than 0, then z would become negative. So that's our minimum bound. And the highest it can get to would be 10, because if it went to 11, x would end up going to negatives. So that is my solution set right there for a parameter t. And then some sample solutions would be, well, if I make t equals 0, I'm going to have the solution 10, 15, 0. If t was 1, we would have 9, 14, 1, and so on. So that's really the way it works. Obviously, this is a lot easier when you do have that line of intersection, which I'm just drawing a box around now, where you can see they're both single coefficients. So there's no numbers there. When that happens, then it can get a bit more complicated. Anyway, it's worth having a go at, though, because it is quite a quick way of getting the solutions out.